Another thing that we're able to analyze within a function is if we see, for example, that the f of a is one sign and that the f of b is a different sign, well, somewhere between positive numbers and negative numbers, there's 0. So what this tells us is that if f of a is one sign, and f of b is a different sign, then there's a 0 for the function, or an x-intercept for that function, between a and b. So in this example, we are finding the interval, the two consecutive integers where we can find a 0 between them. So this is another instance where a table might be helpful. Okay, so we're going to take these values for x, the -3 all the way up to 4, plug them in and find our function values and see where the signs change. So when I take -3 and plug it in, I have 3 squared, which is 9, minus 6, which is 3, over -3 plus 4, which is 1, so that's just 3. When I plug in -2, I have -2 squared is 4, 4 minus 6 is -2, and I'm dividing that by 2, so that's -1. So right away, I see one integer. But I might have more, one interval, excuse me. -1 squared is 1, minus 6 is -5, over 3. So that's still negative. When I plug in 0, I've got -6 over 4. That's still negative. I plug in 1. I have 1 minus 6 is -5 over 5. That's -1. That's still negative. When I plug in 2, that's 2 squared is 4. 4 minus 6 is -2 over 6. That's still negative. Plug in 3. I have 3 squared is 9. 9 minus 6 is 3 over 7. And that's positive, so I see that there's a change here. And finally, they did ask me all the way up to 4, so let's go ahead and test it. So I take the 4, I plug it in, I've got 16 minus 6 is 10 over 8, that's still positive. So my two intervals between which I would find a 0 is I'm going to find a 0 somewhere between -3 and 2 and +2 and 3. In part B, we're doing the same thing. This time, my interval is -5 to 0, so I start at -5. And you're plugging that 5 into that trinomial, or polynomial, so I really hope you have a calculator. So plugging the values in, I have -1000 minus 50 plus 25 minus 1. So it's negative 1026. And one of the things that you might become adept to in your number sense is to think to yourself, you know what, that is really, really, really negative. And when I take this negative 4 and I raise it to the third power and I'm subtracting a whole bunch of stuff from it, I just don't know if I'm going to be getting positive yet. So maybe instead of plugging in negative 4, maybe I plug in negative 3. So again, using my calculator, I've got negative 216 minus 18 plus 15 minus 1. And I'm still pretty massively negative. So maybe I don't want to plug into negative 2 yet. Maybe I want to try negative 1. So I plug in negative 1. And I get negative 8 minus 2 plus 5 minus 1. And I'm getting warmer. I'm at negative 6. And then I'm going to plug in 0. And when I plug in 0, I still have a negative value. Well, I tried to save myself a little bit of time, but I should probably try those other two values and see if there's a 0 kind of sneaking in between there. So I plug in the negative 4. And I've got negative 512 minus 32 plus 20 minus 1. Nope, that's still negative. And it's looking like maybe we don't have a 0 in this interval. Let's double check with that negative 2. And I have negative 64 minus 8 plus 10 minus 1. And no, I don't. So what I've found is that nowhere from negative 5 to 0 will my graph cross the x-axis. Nowhere will I have a 0 between negative 5 and 0. No zeros in this interval. Finally, we come to talking about end behavior. And with end behavior, the main thing that you're looking at is, as I go further to the right, is my graph going all the way up or all the way down, or does it look like it's kind of flattening out towards a number? And the textbook divides them into two categories, graphs that approach infinity and graphs that approach a number. So you see that these examples are titled graphs that approach infinity. And it's asking us to use the function to describe the end behavior. So the way you might want to notate this is maybe with another table. In my table, I'm going to have, as x approaches, f of x approaches. So what I'm looking at is, as x approaches positive infinity, in other words, as x goes further and further to the right, my function values appear to be also going to positive infinity. Because as I go further and further to the right on my graph, I'm also going further and further up in my graph. And so I look at the graph in the opposite direction. As my graph approaches all the way to the left, as x approaches negative infinity, my y's are going all the way down. So my function values appear to be going to negative infinity. And the instructions ask us to support the conjecture numerically. So as something approaches positive infinity, I might choose to pick a very large number to plug in for x. So I might pick an x value of 1,000. If I plug 1,000 in to that function, I've got 1,000 raised to the third power. Is your calculator bursting at the seams yet? And then minus 9,000 plus 2. And so that's a very, very massive number. And what I would hope starts to happen, again, in your personal number sense, is that you realize that if I take a very large number and I plug it into here, that x third, when I subtract that large number multiplied by 9 and then I add 2, that's almost negligible. I could almost ignore that and kind of approximate how huge my number is going to be. So if x is 1,000, y equals a lot, let's say. And if I go in the opposite direction, if I approach negative infinity, if x is negative 1,000, once again, I'd hope that you'd have the number sense to realize that y is a big negative. And so we have supported our conjecture numerically. Doing the same thing in part B. As x approaches positive infinity, f of x approaches. So you're looking at this graph, and as the graph is going further and further to the right, I see that my y values are going further and further down. So that appears to be approaching negative infinity. And as x approaches negative infinity, as I'm looking at my graph going further and further to the left, my function values, my y values, appear to be going further and further up towards positive infinity. Supporting it numerically, if I have x equals 1,000, when I plug this into my calculator, 1,000 raised to the third power, I put a negative in front of it, divide it by 4, that's still a pretty big number, negative-wise. And then I add 1,000 squared times 3 divided by 4 to it. That's still a very large negative number. And because I'm going to have minus a negative this time, I add 1,000 divided by 2, which is 500. I still have a very negative large number. It's actually y equals negative 24,924,000. Oh wait, no. I put my comma in the wrong place. That's how big this number is. So, once again, this is a big negative number. And if I plug in x equals negative 1,000, it's going to go the other way because a negative raised to an odd power is going to stay negative. That's going to be a very large number. So my y value is a lot. Here we're looking at graphs that appear to be flattening out and approach a certain number. And so that gets a little bit more challenging to look at. We might want to use the same kind of table. As x approaches positive infinity, what's happening to f of x? All right, so as x approaches positive infinity, as my graph is going further and further to the right, it looks like somewhere between 2 and 3. And as my graph is approaching negative infinity, as I'm going further and further to the left, it looks like it's somewhere between 3 and 4. So we have something in common here, and maybe we have a hunch about where it's going. And when we look at the equation, maybe that hunch is intensified. But the instructions did ask us to support the conjecture numerically. So I'd like you to be in the habit of at least thinking about what this would look like in your calculator with very large numbers. Okay, so if I plugged in a very large number into this function, what I'd like you to notice is if I plug in a very, very large number, subtracting 2 from it in the numerator and adding 1 to it in the denominator, again, becomes negligible. So I can look at what's happening here. I'd have 3x over x, which would reduce to 3. So if I'm plugging in a very large number, the x's would cancel out and I'd end up with approaching 3. And if I was approaching a very small number, going towards the left, I'd be plugging in a very large negative number, but once again, it would cancel out. Okay, so my end behavior, I can conclude that it's approaching 3. Take a moment and work through your turn below.